I'm Dan. I'm giving the first part of this talk, and I'm going to tell you about how we're doing homotopy theory in type theory. So first of all, homotopy theory is a branch of topology, the study of spaces and continuous deformations. A homotopy, if we have paths here, P and Q, between 2 points there, a homotopy is a continuous deformation between P and Q. And you can also think of this as kind of a two-dimensional path between paths, which is really the perspective on it that we'll take for this talk. And homotopy theory is the study of spaces by way of their paths, homotopies, and then you can go further to homotopies between homotopies, and homotopies between homotopies, between homotopies, between homotopies, etc. Okay, so there's like a nice infinite dimensional tower of stuff there. And so that's homotopy theory. And let me just remind you quickly that one of the reasons that homotopy theory is complex and interesting is even if you look at the spheres, so down here I have like the circle and the sphere, and then the 3-sphere, the 4-sphere, dot, 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 dot. And then here across is what are called the homotopy groups of a space, which is, this is the group of loops in a space, the group of homotopies, the group of homotopies between homotopies. Even for spaces as simple as the spheres, you get this really complex structure. So like, you know, it's kind of wild over there. There's some patterns like it's all zeros here. It's consistent on the diagonal. These diagonals are all consistent. So, you know, there's some patterns that emerge. But it's not like we can just read off what is the kth homotopy group of Sn or something like that. There are still open problems describing these homotopy groups. OK, so that's homotopy theory. What is type theory? Type theory is an alternative to set theory based on the notion of types. And some of the types that we have are basic data types like natural numbers, Booleans, lists, things like that. Then there's a type of functions. For example, the double function has type nat, arrow, nat. And here I've defined it by primitive recursion on the natural numbers, obvious sort of thing. Okay. And the cool thing about type theory is that it unifies sets and logic. So if you do set theory, then set theory has both the notion of a set and then kind of an ambient first-order logic in which you describe set theory. In type theory, there's just one notion of types, and that's because of something called the propositions as types principle. So in the propositions as types principle, a proposition is represented by a type, and a proof is represented by an element of that type. So here I have the type of proofs of equality of natural numbers, and I can prove a simple theorem like for all x in natural numbers, double of x equals 2 times x, where double is the thing that I wrote out on the previous slide that did it inductively, and this is maybe some definition of multiplication. OK, so how do I prove this? Well, I give a program of this type. So I called my program here proof, and proof, maybe if you do a proof by case analysis, that would be represented by a function defined by cases. So when x is 0, well, maybe reflexivity proves the result because we actually compute with the definition of double and 2 times, and they turn out to be the same. OK, so just the flavor of it is that you do proofs by writing programs that have particular types, OK, giving elements of types. OK, so for a long time, we were kind of puzzled by the relationship between type theory and set theory. And to a first approximation, you can think of the type theoretic notion of an element of a type being like the set theoretic notion of x is a member of the set S, and the type theoretic notion that 2 elements are equal as being like the notion of equality in set theory. Okay? But there's a little bit of a mismatch between set theory and type theory, which is that in set theory, an equation is a proposition. We don't ask why 1 plus 1 equals 2. It's just a fact. Classically, it holds or it doesn't. There's kind of not content there. In type theory, every equation has a proof. Okay? And these proofs kind of actually show up when you do your work. And for a long time, type theorists were puzzled by this mismatch between type theory and set theory. But now we have a much better understanding of what's going on here. And it comes from this connection between type theory and category theory and homotopy theory. So based on this correspondence, we know that types, we now like have a better understanding, which comes from the idea that types are not like sets. Types are like an algebraic structure that people consider in category theory called infinity groupoids. Okay? So this mismatch between set theory and type theory, we really have a much better understanding of what's going on. And it's this. Okay, so what does this mean? Well, for one thing, set theory stops kind of at x equals y, but type theory goes on. So you not only have the notion of a proof that two elements are equal, elements of a type are equal, but the notion of a two-proof that proof 1 and proof 2 are equal. So you can ask, are these the same proof or are they different proofs? Then you can ask, are these the same two proofs with a three proof? And so on. So the infinity here is that this just goes on forever. You have this infinite tower of elements, proofs, two proofs, three proofs, dot, 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 dot. Okay? Okay, so what can we do with that? Well, this idea that types are infinity groupoids leads us to a nice interplay between the math and the type theory. So the math suggests new principles to add to type theory. So in this direction, we get new things we can add to type theory that make our lives easier as type theorists. And in the other direction, the type theory suggests new ways of doing proofs in mathematics. Okay? So what do I mean by new proofs? Well, for one thing, we can do computer-checked proofs. So a computer-checked proof, here's a diagram depicting what happens there. There's a tool called a proof checker, and you put homotopy type theory into your proof checker. And then if you're doing a proof, you can write down your proof in such a way that you feed it into this tool, and the proof checker says, yes, that's a correct proof, or no, it's not a correct proof. Okay? So we can do computer-checked proofs. Good. Number two, the cool thing from a more mathematical point of view is that we can do what I'll call synthetic proofs, particularly in homotopy theory. So there's this distinction between synthetic geometry and analytic geometry. Synthetic geometry is geometry in the style of Euclid, where you start from some basic notions, points, lines, and then some axioms that say 2 points determine a line and things like that. Okay? So points and lines are primitive notions, synthetic geometry. In analytic geometry, on the other hand, geometry in the style of Descartes, you think of these things as being represented by coordinates in the Cartesian plane. So it's all very, you're implementing things with coordinates. And classical homotopy theory is really on the analytic side. You think of a space as a set of points equipped with a topology. You think of a path as a map from the interval to the space. Okay? Another example of this kind of thing is that normal analysis would kind of fit over here, and non-standard analysis would kind of fit over here. Okay, so classical homotopy theory is analytic, but what we're doing in homotopy type theory is not this analytic approach. It's really in the synthetic side. So when we do synthetic homotopy theory, we represent homotopy theoretic notions like spaces, points, paths, homotopies by these notions of elements, proofs, two proofs, dot, 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 dot in type theory. So each of these concepts gets modeled as a primitive notion in type theory, just like Euclid modeled points and lines and things like that as primitive notions. Okay, so for example, the first place where people usually get tripped up when we explain this is we don't think of a path as a map from the interval into a space. We think of a path as a primitive notion. Okay? So we have a calculus for working with these paths. What does that look like? Well, I can draw a picture, which is that if we start with a space with 2 points m and n and a path, how does that get mapped to type theory? Well, a space is represented by a type. Points of the space are represented by elements of the type. And paths are represented by proofs of equality of elements. Okay? And the reason this works is that we can derive all the right structure on paths. For example, at any point, there's a little loop here that stands still. Okay, so that's got to be an operation on paths, which I'll call id, which is a proof that m equals m. Why is m equal to m? Well, that's reflexivity of equality. Okay? Similarly, if I have alpha that goes that way, I have alpha inverse that comes back that way. Okay, what is that? That's symmetry of equality. If I have go from m to n and n to p, then by another path beta, I expect there's a composite path beta after alpha that goes like that. That's modeled by transitivity of equality. So this correspondence between paths and equality really gives you the right things here. And you can even prove the homotopies that you would expect between these paths. For example, if I stand still and then do alpha, that's the same as alpha. Alpha inverse compose alpha is id. Composition is associative. And this equals here is the same notion of path. it's a homotopy. It's a path between paths. Okay? So in type theory, we can model the correct structure of paths through this notion of infinity groupoid. Okay, but an important thing to keep in mind is that when we do our work in type theory, like the geometry here really disappears, and all we're left with is the algebraic structure of elements of types and paths and these path operations and homotopies and things like that. Okay, we can only see concepts up to homotopy. Okay, so that's the basics of the approach. The main lesson of this talk is that we can do these computer-checked proofs in synthetic homotopy theory using type theory. And some of the cool things about the approach are that the proofs are constructive, which means we can run them. We'll see good examples of why we want to do that later in the talk. The results apply in a variety of settings, so you can interpret type theory in consimplicial sets, and then because of the adjunction there, transfer our results to topological spaces. You can also interpret type theory in Quillen model categories and as work in progress infinity topoi. So we're doing the proofs at a level of abstraction where they apply in lots of settings, not just topological spaces. And another cool thing is that out of this, we're getting some new perspective on homotopy theory that's leading to some new type theoretic proofs and methods. Okay, and some of this stuff is work in progress. Like, we don't actually know that everything we're doing is constructive yet, but we're pretty convinced it is. And we don't actually know that we can interpret type theory in any infinity topos, but, you know, like, conjecturally something along those lines should work. Okay, okay. So one of the cool things about this approach is that we get both proofs that, this is like a very subjective thing, but we get proofs that feel either more homotopy theoretic or more type theoretic. And for the things we're going to tell you about today, we really had this nice interplay between these, where we started with a very homotopy theoretic feeling proof of pi1 of S1. The fundamental group of the circle is Z. And then out of that, by analyzing that, got a more type theoretic one. Okay? And then later on, we got a more homotopy theoretic feeling proof that the total space of the total space of the Hopf vibration in pi2 of S2. And then from there, we kind of analyzed it and got a more type theoretic feeling one. It turned out that the type theoretic one was easier to formalize and to generalize to pi n of Sn. But then kind of pulling back in the other direction, we got one that's sort of in the center of the Freudenthal suspension theorem that really mixes some type theoretic concepts, some homotopy theoretic concepts. And then out of that got another proof of pi n of Sn that is sort of in the center. So there's really been this interplay between people who know the mathy side, people who know the type theory side. And I think without having the opportunity to all be here in the same place this year, we would not have gotten these sorts of things. Okay, so what we want to tell you about in this talk is basically this tower of results. So we're going to start with a proof that the fundamental group of the circle is Z, which is going to introduce some of the basic concepts. And then Guillaume's going to tell you about the total space of the Hopf vibration, and Peter's going to tell you about the proof of the Freudenthal suspension theorem. Okay, good so far? Okay. Pi1 of S1. So to represent the circle, we use something called a higher inductive type. And the idea is that we say that the circle is inductively generated by a point base and a loop around it. Okay? So up to homotopy, the circle has a point and a loop. And when we say this, we put in generators. Base is on the circle, and loop is a path from base to base. So we generate it by one point and one path. And then when we say, I would like the space inductively generated by this stuff, what we get is the free infinity groupoid with these generators. So even though we just started with base and loop, we then, for free in a sense, get the identity loop here, loop inverse that goes that way, right? We put in id and loop inverse and loop composed loop, and then a path from loop composed loop inverse to id, all of the structure, right? So all the structure kind of comes for free, okay? And the key thing about saying that the structure comes for free is that you get a universal mapping property for maps out of the circle. So when we say that the circle is inductively generated by a function, is inductively generated by base and loop, that is to say that when you want to map the circle into some other space, it suffices to give a point and some possibly crazy loop in that space. Okay? So there's a function from the circle to the torus. It sends that to that, okay? So to give a function from the circle into a space X, it suffices to give a point in X and a loop in X, okay? So the way that we work with circles is by this way of making functions. And the way we prove things about circles is by a corresponding principle of circle induction, which says that to prove a predicate P for all points on the circle, it suffices to prove it for the base point as long as that proof that you give is continuous in the loop. And that notion of continuous in the loop gets made very precise in the type theory. Okay, so that's higher inductive types. That's one of our key tools. And so now we'd like to prove that the fundamental group of the circle is the integers. So we define the loop space of the circle, omega of S1, to be the space of loops at the base point, okay? That is, it's the type of paths from base to base, which is represented by the equality type base equals base, okay? Okay, that's loop space. And what we can prove is that the loop space of the circle is equivalent to the integers by a map that sends composition to addition. Okay, how do we prove this? Well, we can define two mutually inverse functions, winding, which takes a loop on the circle and computes its winding number, and loop to the n, which takes a number and spins around that many times in that direction if it's positive, or n times in that direction if it's negative. Okay, so we just write down the functions, and then we prove that they're mutually inverse. Okay, as a corollary of calculating the loop space of the circle, we get that the fundamental group of the circle is isomorphic to Z, okay? And the reason is that we define the fundamental group to be the zero truncation, or the set of connected components of the loop space. So if we know that the loop space is Z, then we also know that when we take the zero truncations, that preserves that equivalence. And the zero truncation, or the set of connected components of the integers, is just the integers. So we get that the fundamental group is Z, okay? We also get a stronger statement as a corollary, which is that pi k of S1 is trivial when k is anything other than 1. And that's because all of the higher homotopy groups of Z are provably trivial. Okay? So the thing to really zoom in on is this fact. The loop space of the circle is equivalent to Z. Okay? How do we prove that? Well, the interesting part is really that I'm going to focus on here because we're short on time, is just how do you define this winding map? How do I take a path on the circle represented in this theory of infinity groupoids and compute a number, okay? And the way that I do it, well, the way that Mike did it really, is very much the same way one would do this in classical homotopy theory. You define something called the universal cover of the circle, okay? What is the universal cover of the circle? It's a helix sitting on top of the circle, okay? And the key property of this is that you can lift a loop in the base up to the total space, up to the helix up here, okay? So if you give me some loop that winds around the circle some number of times here, what I'm going to do is I'm going to lift it upstairs and then look at the other endpoint of 0, okay? So the key properties of this lifting are that, number one, it's functorial. Number two, when I lift the loop, I go up one level in the helix. And when I lift loop inverse, I go down one level in the helix. Okay? So if I have a path like loop compose loop inverse, right, I want that to turn out to be 0. Why does that turn out to be 0? It's because when I lift loop compose loop inverse, it's functorial, that is, it commutes with this composition. And when I lift loop, I get +1. And when I lift loop inverse, I get -1. Therefore, I get 0 + 1 - 1, which equals 0. So this lifting up to the cover is what straightens out the, like, I go that way and then I immediately come back kinds of compositions, because +1 and -1 cancel. OK, so how do we represent the universal cover in type theory? Well, the universal cover is an example of what's called a fibration. Okay? In general, a fibration is a map P from E to B such that any path from P of E, where E is upstairs, lifts to, and P maps it downstairs, lifts to a path in E from little e to some point in P inverse of y. Okay? So in this example, E is the helix, B is the circle. And what this is saying is that any path from, and okay, P is sending each of these points down to the base. And what this is saying is that any path from base to somewhere else on the circle lifts to a path from any of these points lying over base to something that's in the fiber over wherever the other endpoint of the path is. Okay? So classically, fibrations are kind of a technical thing to define. But really what they're getting at is the notion of a space parametrized by another space. And this notion is representable really directly in type theory. We represent fibrations as what's called a family of types. So we can have a family of types E of x for x and b with the idea that okay, so like what do we have when you have a family? You have the notion that for everything in the base, E of b is a type. Okay, so what is that type? That's, you think of that as the inverse image of the point in the base. Okay, so here I have base, and then E of base would be this collection of integers lying over base. And the other thing that you have when you have a fibration is this path lifting that I was describing up here. And that gets modeled in type theory by the fact that whenever you have a path from B1 to B2 in B, that determines an equivalence between the fiber over B1 and the fiber over B2. And we write that equivalence as a function called transport. Okay? So in this particular example of the universal cover, the transport is, the way to think about it is that it sends E in E of x to the other endpoint of the lifting of the path. The path lifting determines this equivalence. So the way that we do this in this particular example is that we would like to define the universal cover as a family of types over the circle. Okay? We want to represent that picture as a family of types over the circle. Okay? But we know by circle recursion that to give a family of types over the circle, it suffices to give the fiber over the base point, which is the integers, and for the lifting, to say what happens when you lift the loop as an equivalence between z and z. Okay? So this is where we're using Vladimir's univalence axiom to say that paths in between types are the same as equivalences. That's, okay, so it suffices to give an equivalence between z and z as the lifting of the loop. And in the example, we reason through when we lift the loop, what we would like to do is to take it to the successor function. Okay? So the code that we get, the definition of the cover, is that we say that the cover's fiber at base is z. It's 0, 1, 2, dot, 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 sitting over base. And that when we have this transport function, which says what happens when you lift the loop, that's successor. Okay? So there's this really nice way of defining fibrations just by giving the fibers and what happens when you lift the paths. And then the real win from this kind of way of working with fibrations is that we can calculate with them. So a lot of the proofs that we do involve calculations using these defining equations. For example, we can define that winding map that I was talking about before, which is the one that lifts a path on the circle up to the cover, by saying, give me a path on the circle. What I'll do is I'll lift it up to the cover and take the other endpoint of 0. That's written transport cover P starting with 0. Okay? And then we can calculate in the example of, like, if I go that way and then back that way, why does that turn out to be 0? Well, by definition, the winding applied to this is take this path, lift it up to the cover, and give back and apply it to 0. Then we know generically that transport is functorial. So I can push it inside and say that it's lift loop inverse up to the cover, lift loop up to the cover, apply it to 0, okay? And then by definition, by the defining equation for the cover, when I lift the loop up to the cover and apply it to 0, I get 1. And then by the defining equation, sort of inverted, when I lift loop inverse up to the cover, apply it to 0, or apply it to 1, I get back to 0, okay? So we can do this kind of thing just by calculating using this definition. This is, in fact, really the same moves that you make in 1/2 of the proof that this map composed with the one that just spins around n times is the identity. Okay, so that's the definition of the winding number. Just so you can get a sense for the scale of it, here on the left is the scope of what it looks like to take this proof that I was just telling you about of pi1 of S1. And when we wrote it out in the book about informal homotopy type theory, it was, about 4 pages of stuff. On the right, we've got the computer-checked proof, the one that's actually running in our proof assistant of the same thing. And the thing to really take away is that these are really, comparable in size. Often when you do computer-checked math, there's this big blow up. It's like 5 to 10 times longer. But here we're getting something that's really comparable. And I think the real reason for this is this synthetic approach to homotopy theory. And we really get our hands directly on the structures we want to talk about. And that leads to these nice formalizations. OK, so that's the end of part 1. Now Guillaume's going to tell you about the Hopf fibration.
Oh, thank you, Dan. So Dan explained how to get pi1 of S1 equals Z in homotopy type theory. The main idea was to construct the universal cover of the circle using the definition of S1. So in this part, I will talk about a different fibration called the Hopf fibration. And with the Hopf fibration, we will see how to prove that pi2 of S2 is the group of integers again, and a few more results. So what is the Hopf fibration? The Hopf fibration is a fibration with base S2, the 2-sphere, fiber S1, the circle, and total space, the 3-sphere. So again, in ordinary homotopy theory, you define a fibration to be a map with some property, and you think of this map as a family of space depending on another space. So really, the Hopf fibration is a family of circles parameterized by the 2-sphere, S2, and whose union or gluing or total space or whatever is S3. So you imagine you have the 2-sphere and the family of circles depending on the 2-sphere. You can glue all these circles together, and you should get the 3-sphere, S3. So we'll explain how to prove, how to construct this Hopf fibration in homotopy type theory. So first, a picture of the Hopf fibration. So this is the 3-sphere. This is R3 plus a point at infinity. And you have a bunch of circles. So if you look, you have one red circle like that, and one circle which looks like a line because there is a point at infinity. And then there is some torus. If you want, you can see each torus as a circle of circles. So you have one red circle, one other red circle, and then a bunch of circles going from the first one to the second one. So we cannot do that directly in homotopy type theory. We need to write formulas in some way. Well, so we'll need to use the synthetic approach to define the spheres and to define the fibration. So first, what is the definition of a sphere? So we first define what is the suspension of a space. If you have a space A, the suspension is, again, like the circle, a higher inductive type, which is a type generated by the following data. You have 2 points, north and south, corresponding to the north and south pole. And then for every point in A, you have a path M of A, meridian of A, which is a path from the north pole to the south pole. So for instance, if A is a circle like that, the suspension of A, you have the north pole, the south pole, and then a circle of paths between north and south. So if A is a circle, the suspension looks like a 2-sphere. If if you take A, a 2-sphere, the suspension will look like a 3-sphere. So you can just define the n+1 sphere to be, by induction, the suspension of the n sphere. And then already define what is the circle. OK, so we want to define the fibration over the 2-sphere. How do you do that? The 2-sphere is defined by 2 points and a circle of path between them. So to define a family of type depending on the 2-sphere, you need to say what is the fiber over the north pole. So you need to give a space A, the fiber over the north pole. You need to give a space B, which is the fiber over the south pole. And then you need to give a circle of equivalences between A and B. So in other words, you need to give a function E from S1 to the type of equivalences between A and B. Or if you prefer, for every x in S1, you give an equivalence E of x from A to B, which will correspond to when you transport along the meridian corresponding to x, you have an equivalence from the fiber over the north pole to the fiber over the south pole. So you need to give this family of equivalences.
This is using univalent.
Yes. Yes. Again, using the usual property of the circle, you need to give a path between A and B in the space of all spaces. But the univalent axiom tells you that a path between 2 spaces is exactly the same thing as an equivalence between the 2 spaces. OK. So we want the up fibration. The up fibration is a fibration over S2 with fiber S1. So we need to give the fiber over the north pole. So we give S1, because we know the fiber is supposed to be S1. Then we need to give the fiber over the south pole. Again, we give S1, because it's still supposed to be S1. And then for every x in S1, you need to give some equivalence between S1 and S1. So obviously, you could do something stupid, like for every x, take the identity function. So you will get a fibration over S2 with fiber S1, but it will be a trivial fibration, and the total space has no chance to be S3. So if you want the up fibration and want the total space to be S3, you need to do something else. And what we'll do is the following. For x in S1, the equivalence corresponding to x will be the rotation of angle x in the circle. Or you can see that at multiplication by x or addition by x, according to how you see the circle. OK, so what do we have to do? We need to define what is this rotation of angle x. Because the circle, again, is defined just by a point and a circle. You cannot say the circle is the set of complex number of module 1 and then use multiplication. You need to define it synthetically with the definition of the circle as 1 point and 1 loop. And then we'll want to prove that the total space of this fibration is the 3-sphere. OK, so we want to define the rotation of angle x in the circle. So what this is a function, takes a point in the circle, and gives back an equivalence between S1 and S1. So you see E of x is the equivalence corresponding to rotation of angle x. By definition of S1, S1 is defined with a point and a loop. So to define a function like that, you only need to give a point in this type, which is what happens if you have a rotation of angle, the base point of the circle. And then you need to explain what happens for the loop. So you need to explain the rotation of angle, the base point, and then when you go around the loop, you get a homotopy between this E base and itself, and you need to define this homotopy. So what do we take for E base? It should be the rotation of angle, the base point. So we can assume the base point is 0 or whatever. The rotation, the value of E base will just be the identity function. Makes sense? OK, so this one is the identity function. And now we need to construct a homotopy of the identity function to itself. And the idea is that we'll define the homotopy which do one turn around the circle. So you have the identity function, and you want a homotopy of the identity function to itself. You will take the homotopy which does one turn on the circle. Okay, how do we define this homotopy turning once around the circle? So what is a homotopy from the identity function to the identity function? By definition, a homotopy is just a pointwise path. So you need for every x in the circle a path from x to x. If you have a homotopy, you can apply this homotopy to any point x, and you get a path from x to x. So this is what we need to define. How do we define that? Well, once again, the circle is defined to be the type generated by one point and one loop. So to define that, I need to do it when x is the base point and do something for the loop. So what we need is, when x is the base point, we need a path from the base point to the base point. And when x goes around the loop, so if you look at the formulas, you get something like that. You need a two-dimensional path between p compose loop and loop compose p. So this is a concatenation of paths. And you can see that as some sort of naturality square. You need the path that you give for the base point should be compatible with the loop in the circle. And it turns out that this is what you need. OK, so what path p should we take? Again, there are a lot of choices. You can take p to be the constant path, and q will be, again, the constant path. But then it will not be the homotopy turning once around the circle. If you want the homotopy which turns once around the circle, if you look at the base point follows exactly the loop in the circle. So you want to take p equals loop, the generating loop in the circle. And then q should be a two-dimensional path from loop compose loop to loop compose loop. Well, that's not difficult. You can take the constant path between the two, corresponding to the reflexivity proof, if you want. OK. So now we finished to construct the Hopf fibration. We constructed a fibration with base S2 and with fiber S1, and in some way which doesn't seem trivial. But we still need to compute the total space. So the total space should be S3, and we need to prove that. OK. I will first need to define a notion of homotopy push-out. So given a span, so you have 3 spaces and 2 maps like that, you can define the homotopy push-out of this span. So the idea is that you have y on the left. So for every y in y, you have a point. You have z on the right. For every z in z, you have a point, r of z. And then for every x in x, you add a path between f of x and g of x. So you have y, z, and then a bunch of paths parameterized by x. Again, this is a higher inductive type, where you define a space by giving generating points and paths. So for instance, the suspension of A is actually a special case of homotopy push-out. If you take y and z to be the one-point space, the homotopy push-out of this diagram is just you have 1 point on the left that you can call the north pole, 1 point on the right you can call the south pole, and then for every element of A, you have a path from the north pole to the south pole. OK. So now, if you remember the construction of the Hopf fibration, what we did is we start from the 2 sphere, which has north and south, and then a circle of paths. Above the north pole, you put the circle. Above the south pole, you put the circle. And in between, you do something with the rotation of angle n. So by very general lemmas, gluing, descent, or flattening, whatever you want to call it, you can show that the total space is the homotopy push-out of this diagram. So this diagram, you have S1 on one side, S1 on the other, and then some torus of paths between them using this E. So this E was this rotation of angle x in the circle. So you can easily prove that this total space is the homotopy push-out of this diagram. And then, by looking at the definition of E and checking that E is well behaved, you can prove that this span is equivalent to this one. So the P2 was the second projection from the product. So you can prove that it's equivalent to this span with the product S1 times S1 in the middle, and then first projection and second projection. So you get that the total space of the Hopf fibration is the homotopy pushout of this diagram. And the homotopy pushout of such a diagram is called the join of S1 and S1. So more precisely, if you have A and B two spaces, you can define the homotopy pushout of the diagram with A times B in the middle and the two projection. And the pushout of this diagram is called the join of A and B. The idea is that you have A on the left, you have B on the right, and then for every point in A and every point in B, you glue a path between them. And this is called the join. So there are a few properties of the join. For instance, the join with S0 is the suspension. So S0 is the zero-dimensional sphere. This is just the type with exactly 2 points. So if you imagine you have 2 points on the left and then A on the right, and you glue a lot of paths in between, what you get is two cones on A glued together at A. So what you get is exactly the suspension. So that's not difficult to prove in homotopy type theory. You can just write the two maps back and forth and prove that the two compositions are the identity, and that's it. Slightly less trivial, the join operation is associative. So this is a bit more technical to prove, but this is not very difficult either. Okay, so now we can compute the total space of the Hopf fibration. We knew that the total space was the join of S1 and S1. Now S1 is the suspension of S0. That's not difficult to prove. Then suspension of S0, replace it by a join with another copy of S0. Use associativity of join. Then suspension of S0 is the suspension. And double suspension of S1 is S3 by definition of S3. So we have the Hopf fibration in homotopy type theory. What can we do with the Hopf fibration? Well, we can compute some more homotopy groups of spheres. So for instance, whenever you have a fibration, there is a long exact sequence of homotopy group associated to it. So on the first column, you have the fiber of the fibration. On the second column, you have the total space. On the third column, you have the base. And you have some connecting maps like that. And you can prove that you get an exact sequence of groups, even abelian groups in this case. So you can easily prove that in homotopy type theory too. So now we know some things about that. First, in Dan's part, Dan computed all homotopy groups of S1. So we know that pi 1 of S1 is Z, and that all pi k of S1 are trivial. So we have this column. Also, we can prove that pi k of Sn is trivial for k less than n. So we will not talk about that today, but you can easily prove pi 2 of S3 is trivial, pi 1 of S3 is trivial, pi 1 of S2 is trivial. So you get 3 zeros in this place. But now we have an exact sequence of groups of the form 0GH0 and 0GH0. And as you probably know, it means that all these maps are equivalences, isomorphisms of group. So what we get is pi 2 of S2 is Z. And for all k at least 3, pi k of S3 is pi k of S2. So pi 2 of S2 is Z, and pi k of S2 is pi k of S3 for k at least 3. So we have the next group, homotopy group of sphere in the diagonal. And we have a few more results. For instance, assuming that we have pi 3 of S3 is Z, so Peter will talk about that in a few minutes. Assuming we have that, then using this equation, you get pi 3 of S2 is Z as well. So we get the first non-trivial homotopy group above the diagonal. Okay? And So before letting Peter talk, I will I want to say a few words about pi4 of S3. So pi4 of S3 is the next non-trivial homotopy group above the diagonal. And using the same kind of synthetic homotopy theory method, you can prove the following theorem. There exists a natural number n such that pi4 of S3 is equal to z mod 2. So the question you probably ask is, what is n? So in classical homotopy theory, we know that n is 2. So it should be 2. But so what we prove is that there exists a natural number n with some property. What can we do with that? If you're in classical mathematics, in general, you cannot do anything with it. Knowing that there exists an n with some property doesn't tell you how to compute the value of n. The best you can hope is, let's look at the proof of that. And if the proof is nice enough, maybe I can extract the value of n in this proof. But if, for instance, you prove that by saying, assume there is no natural number n like that, then contradiction, so there ought to be one somewhere, then it doesn't tell you how to compute it. But the point is that in homotopy type theory, in particular in the proof of this theorem, we're not doing classical mathematics, we're doing constructive mathematics. In constructive mathematics, you disallow some form of reasoning. For instance, you're not allowed to use the axiom of choice, or you're not allowed to use the law of excluded middle, which says every proposition is either true or false. So you're not allowed to use that. But far from being a restriction, you get a much nicer system. In particular, an important meta-theoretical result is that every proof is nice enough, in the sense that every time you prove that there exists a natural number n having some properties, then you can actually extract the natural number from the proof. And in this case, this proof is constructive, so we can compute the value of n and get 2. So as Dan said, little caveat, the fact that homotopy type theory is still constructive is actually still a conjecture. And we don't understand the algorithm well enough to be able to apply it in this special case. But, well, it's widely believed that homotopy type theory is constructive and that we will get the value of n to be 2.
Or minus 2. We'd be equally happy with minus 2.
I said the natural number.
Oh, you said that.
Yes, it could be minus 2. Okay, so now Peter will talk about Freudenthal suspension.
Good, excuse me. There we are. Thanks, Guillaume. Dan and Guillaume have nicely laid out some of the special cases of computing with some specific, very concrete spaces. And now I want to kind of move on from there and start looking out to the bigger picture of how we can move to some of the general theorems of classical homotopy theory and prove them also in this setting. So in particular, to develop the machinery of truncatedness and connectedness and the Freudenthal suspension theorem. And the lovely thing here is that all of these general machinery, just as much as working with very specific spaces, all still works with the same kinds of elementary, very concrete type theoretic methods that Dan and Guillaume have shown so far. So one is still playing with elements, defining functions by cases, all that sort of thing. It keeps expanding in all the directions we've pushed it so far. It goes nicely. So to get to the suspension theorem, we need to define some of the machinery, some of the general concepts and properties that are classical ideas of homotopy theory, and also very natural in the type theoretic setting. So first, truncatedness is the one which is the lowest hanging fruit to define. So this is the idea that a space is, in some sense, a low-dimensional space. So we say that a type is n-truncated or the more classical terminology is that it's an n-type. We define this by induction on n starting slightly oddly at -2. Many things for dimension indexing seem to start at -2. We say it's -2 truncated if it's contractible, if it's equivalent to a point. And then for higher n, we say it's n truncated if each of its path spaces, each of its path types, is n-1 truncated. And certainly if you've got this, then you can reasonably straightforwardly prove that all the homotopy groups above the level of truncation are trivial. One might think that one could prove the converse, or could have even taken the converse as a definition of this. And in classical settings, in some of the main classical settings like topological space or simplicial sets, that certainly does hold and is often taken as the definition. But it doesn't actually hold in all classical settings. So there are, it's a property of infinitopoi or Quillen model categories known as hypercompleteness. And we don't expect that homotopy type theory insists that the setting is hypercomplete. We expect that to be something where we could model type theory in non-hypercomplete settings. And so we don't expect to be able to prove a converse for this proposition. So we take this as the definition, and then this is a handy corollary. So then we, having got truncatedness and this property of being truncated, being trivial in higher dimensions, it's very handy to generalize the idea which we already saw in the case n equals 0, and discussed the set of connected components which one uses when defining the homotopy groups. The set of connected components of a space is the free way of turning the space into a space that's essentially just a set, essentially just a discrete set, something that has no higher homotopy at all, no non-trivial paths or loops at all.
So, question, for which value of n is a discrete set and truncated?
Good. So a discrete set is exactly the same as a zero truncated space, or a space is equivalent to a discrete set exactly if it's zero truncated. And truncation is monotone, so it's zero truncated and then automatically also truncated for all higher values. So that's the two most important examples of truncatedness are probably n equals 0, which gives exactly the essentially discrete spaces, and then n equals -1, which gives the things which one can think of as kind of mere propositions, things that just have the information of whether they're true or not, whether they're inhabited or not, and don't have any distinct elements one could look at. And so we had this idea that you could take any space and look at its set of connected components, so forget any loops, any higher homotopies at all. And we can do that for any dimension, in fact. We can take, for any n at least -1, the n truncation of a type to be, we want it to be the free n truncated type on X. And we can actually construct this as a higher inductive type by saying we simply throw in any element of X itself as an element of its truncation. And also, if we had any high-dimensional loop, high-dimensional homotopy in the space, we insist that that should be constant. So any map from a suitably high-dimensional sphere into the truncation has to be a constant map. And so this lets us use higher inductive types of the sort we had before to construct the free n-truncated type on any type. So a property that any map from X into some truncated type factors through this truncation. I said here for n at least -1, one can construct the truncation also in the case n equals -2, but this definition doesn't quite work. It looks slightly different in the base case. So classically, one can think of this construction as we're simply iteratively gluing higher dimensional cells onto X to kill all its higher homotopies. Now, I skipped over a slide, excuse me. Oh no, sorry, I didn't skip over a slide, beg your pardon. So having defined truncatedness, there's a dual notion to this, and we'll see shortly how it's dual, which kind of plays off against it classically And the interplay between the two is the source of a lot of very powerful results, which is connectedness of types and more generally of maps. So we say that a map is n-connected if its truncation at the n, its n+1 truncation is contractible. So for instance, the circle is, I beg your pardon, I got an index wrong here. This should be the n truncation. Right. The circle is zero connected. The zero truncation, when we kill the circle to get a discrete set, that's contractible. So the set of connected components of the circle is just a singleton. So a space is connected if its n truncation is contractible. And there are several equivalent ways one could characterize that. It's n-connected exactly if every map from it into any n-type is constant. So one can see this is simply the universal case of a map from X into an n-type. And also one can characterize it in terms of homotopy groups. And in this case, it really is, unlike truncatedness, it really is an equivalent characterization. A space is n-connected exactly if all its homotopy groups from above the dimension where it's connected are trivial. So we had connectedness.
Below.
Sorry?
Below the dimension where it's connected.
Below the dimension where it's connected. This slide I am saying all the things the wrong direction. Yes, so connectedness, we're saying that a space has trivial lower homotopy groups, and truncatedness, we're saying that a space had trivial higher homotopy groups. So that's one kind of imagery of how the two are dual. But a slightly more precise formulation of the duality one can get by moving to the idea of connectedness of maps. So we can say that any map is connected exactly if each of its fibers is, as a type, is connected. And of course, when we say fiber, we mean homotopy fiber because everything in our logic is invariant under homotopy. So when we say fiber, we mean homotopy fiber. So we define a map to be n-connected exactly if each of its fibers is n-connected as a type. Little caveat here, there are the indexing conventions for this vary between different schools and approaches to homotopy theory. So if you're comparing the theorems we prove about this with ones that you see elsewhere, you may need to add or subtract plus or minus one somewhere. And again, one can look at this several different ways. A map is connected exactly if it's orthogonal in the sense of a lifting property to maps whose fibers are truncated. And so this is a strong statement of the duality, that whenever you have a square, a commutative square with a connected map on the left and a truncated map on the right, so a map that we can think of as a family of truncated types over X, then one gets a diagonal lifter, a diagonal filler, a lifting in the middle of the square. And in fact, if one has the liftings at all, it follows that they're unique, just because the path spaces, the equalities that one wants to show for their uniqueness, there are equalities in truncated types, so they themselves are even more truncated, and so one can simply apply the same thing again to get uniqueness. And this sort of lifting property is something that's very practical indeed to work with in type theory, to work with concretely. Because it's saying we're trying to define, typically you use them when one wants to define the filler. So one wants to define some map out of B. And it's some map into an n-truncated type which may depend on the element of B. So we're trying to define for everything in B something in some n-truncated type. And this says it's enough to define it just in the case of things that came from A. So we've got the n-truncated types. If we can define our function in the case of something that came from A, then that gives us the commutative square. So it gives us the filler. It gives us the definition of our function for everything from B. And this is very familiar to type theorists, this sort of thing. It looks just like the kind of induction principles that inductive types are defined to satisfy in the first place, except with the restriction that it's for mapping into truncated types. And another equivalence one can give, and one which is not so useful in practice but very helpful intuitively, or at least I've never we've not yet run into places where it's been what we've wanted in practice, is that that a map is connected exactly if one can see B as up to equivalence. B can be thought of as an extension of A by high-dimensional cells, by cells of dimension more than the connectedness of the map. And one can see that why the connection arises in at least one direction here by saying if B is an extension of A by just gluing on some higher dimensional cells along their boundaries, then in a square like this, well, to map out of B, one has to map out of A and then also map out of those cells one's glued on. But now one's mapping out of high-dimensional cells into a truncated type. And within the truncated type, the high-dimensional cells are going to be saying, show that higher-dimensional maps out of spheres are trivial. But we know by definition in a truncated type that higher homotopy is trivial. So that's one direction of this, and this is a helpful intuition for some of the results about these. In particular, it's helpful for seeing what's going on in this result, the connectedness of the inclusion of the wedge into a product, which it's a sort of innocuous-looking lemma. It's a kind of simple statement about a simple couple of spaces, but it's one that's very, very convenient indeed in practice. So this is the first place where additivity of dimensions comes into anything we've done. So the theorem that is, if you've got a type x and a point x0 within it, so a pointed type, and if the type x is I-connected, and you've got another pointed type y with y0, and it's j-connected, then you look at the inclusion of the wedge of x and y, which is the homotopy push-out, x together with y glued together at their base points, into the product. So this inclusion, one can think of x and y as being something like the reals, and then the product is something like the plane, and the wedge is like the axes in the plane. It's two copies of the reals glued together at the origin where they meet, glued together at their base points. And the theorem says that the inclusion into the product is I plus j connected. So where does the additivity come from? The additivity is just because one can think of it as to build the product up. So if the space was built up out of low-dimensional cells, so for instance in this case, from the base point, x is built by adding on a one cell, y is built by adding on another one cell. When one's building up the product, then these one cells become one cells from the wedge together with a two cell mediating between them. And so the additivity of dimensions is that these one cells combine to give a two cell between them, just like Rn times Rm is Rn plus m, thinking vector space-wise. But type theoretically, what this means in practice, and the reason why it ends up being so handy, is that it tells us to define a function of two variables, x and y, when x and y are suitably connected types. So defining a function out of the product into some truncated type, we just have to define it on the wedge, which means in practice we just have to define it in the cases where one or other of the variables was the base point, and then check that these two definitions agree in the case where both were the base point. So anytime we've got connected types and we're defining a function of two variables, we can do it in the cases where they were the base points. And we have this additivity of dimension. We can do it for maps into a I plus j truncated type. And there are also versions of this with more than two spaces. So if you had, say, a function of 5 variables, then you can do a similar thing for adding the 5 different connectivities. And now this gives the key, this is the kind of key background lemma that we need to approach the Freudenthal Suspension theorem using the same sort of methods that we've seen already. So what is a suspension theorem? Recall from what Guillaume said that the suspension itself is taken from any type by you add in a north pole, you add in a south pole, and then you add in a meridian, a path from the north pole to the south pole for each point of the space itself. So we can see it, if we think of x as looking something like the circle, then we can visualize this as a globe. But another way to, a sort of more algebraic way to think of it, is that it was the free way of putting x into a path space. It's kind of the minimal possible way to get some path space and a map from X into the path space. And one can make that precise as a universal property as well. But we can ask, if we've put X into a path space and done it as freely as possible, how close is that map to an equivalence? Could it be that the path space we got looks exactly like X? So when we look at the map from X into, we can either take the path space from north to south, or traditionally it's more usually stated using the loop space from north to south, where one can identify the two by simply going back along the meridian at the base point of the Greenwich meridian. So we want to say the map from X into the loop space of the suspension, could that be an equivalence? When we freely put X in, did we get anything more? Generally, it certainly isn't. And we just need to look at low-dimensional examples of spheres to see, OK, it definitely isn't in general an equivalence. When we put the, for instance, the one sphere into the two sphere, one knows from classical topology that the two sphere, it blows up kind of crazily the complexity of its homotopy in higher dimensions. And as we saw from Guillaume, we've kind of already seen enough to start proving how it's non-trivial in higher dimensions. So whereas S1, one can prove that this is just a one type. This is truncated and not trivial in higher dimensions. So in general, this certainly isn't an equivalence. Freudenthal says, well, here's what we can say about it at least, that the map, that this inclusion map is going to be highly connected, assuming that the space we started with was somewhat connected. So, so it's not necessarily an equivalence, but it is an equivalence within a certain range of dimensions. So this is very useful, in particular in the case of spheres, keeping homotopy groups of spheres as our kind of guiding theme of applications. Since the spheres were all suspensions, it's straightforward to see, and we'll say precisely how later, that this will end up telling us quite a bit about their homotopy groups. So how do we show this? The full proof of Freudenthal gets a bit more technical and uses some slightly different techniques. So I'll prove for now, I'll give the proof just for now of a slightly weaker form, which is saying that not that inclusion map from X into the loop space of the suspension is quite connected, but that when we truncate it at the 2n level, we get an equivalence, which is close to being 2n connected, but slightly weaker. And the proof, we use the heuristic which was implicitly there in, for example, Dan's proof of the loop space of the circle, which is the heuristic that if you're trying to prove something about a path space, in particular, if you're trying to show that some other type is approximately equivalent to the path space, to a loop space or something, your life's going to be a lot easier if you can generalize it so that you're not asking a question just about the loop space itself, but about the family of path spaces where one or both endpoints is able to vary of your space. So instead of just trying to prove that X is equivalent or up to truncation equivalent to the loop space, we'll generalize X to a dependent type, X bar, over the suspension. And so that in particular the fiber at the base point was the type that we wanted to start with. And then we'll prove that equivalence for all the path spaces and recover the original result we want as a special case. And this is something that will be not that surprising to type theorists when one thinks of equality as having a bit of a universal property, which we haven't mentioned but is the kind of defining characteristic of equality in this setting that one starts from. The universal property, one can use it when one has this fibration over all the path spaces. So this is, one can use it as transport. One can transport around within this fibration. And when one just had the single X, one can't transport. Once one generalizes it to a fibration, a dependent type, one can transport. So in this particular case, we want to define a dependent type over the suspension of X, and then maps from there into the truncated path spaces using the universal property of the suspension. So this is again just like how Dan defined the universal cover of the circle, by using the universal property of the circle. So concretely, what does this mean, looking at the universal property of the suspension? This means that we need to give things for an arbitrary point of the suspension, we need to say what they do at north and at south, and then we need to say how they act along the meridians of the suspension. So we need to say how things transport between the values of the fibration at north and south. And so we know from the original theorem we wanted what we wanted to do at north and south. At north and south, we wanted to show that the 2n truncation of x was equivalent to the 2n truncation of the path space or the loop space. So we use that as our definition of the values of x bar there. And also, we knew what the maps to the path space should be because we had the meridian, which mapped x into the path space. So we take the truncation of the meridian map, and then the map into the loop space that I described, where one takes a path from north to south and coerces back canonically by going along the Greenwich meridian backwards. So this gives us how we map our fibration into the path spaces at north. And now we need to say what the transport does over the meridians so that we can transport around this fibration. So we need to define an action. So for each meridian, for each m of x of some x from x, we need to define a transport function along there going from the value of our fibration at north to its value at south, which we had concretely defined here. So that's saying we need to give for each element of x and an element of the truncation of x some other element of the truncation of x. And so and at this point, the type theory practically proves it for us. One simply uses universal properties again and again. This is where the kind of elementary method gives something that almost, if we had a little bit of better proof automation in our proof assistance for these, could well come as an automatic proof. We're mapping into a truncated space, and we're mapping out of a truncation of x. So we may as well map out of x itself, since this was the free truncated space on x. So we can assume that z came from some x2 in x itself. So now we're saying we've got x1 and x2 in x, and we're trying to give something in the truncation of x. And now, this is where we get the 2n coming in. We're mapping into a 2 untruncated thing out of two variables from a connected space, from an n-connected space. So we can use the wedge into the product to say it's enough to do it in the case where one of these two things was the base point. So let's see. So if this was the base point, then we can just give back that one. And if this was the base point, we can just give back that one. So either way, when one is the base point, we give back the other. And this we can see as roughly, we're kind of like defining a multiplication on x for which the base point is a unit on either side. And we can't really do that on x itself, but we can do it once we truncate the right-hand side. So we can get, so this is a multiplication not quite from x to itself, but from x and its truncation into the truncation with the base point as a two-sided unit for it. Since when either of these was x0, we said the multiplication is just the other one. And the truncatedness-connectedness interplay now directly tells us that extends to define on all other pairs. As soon as we said we wanted x0 to be a unit, then we're good. Then we get it for everything else automatically. So this was exactly what we needed for the transport. And so it gives us our fibration mapping into the path spaces. Now, that tells us we're able to so we have this dependent type, we can define our putative converse from the path spaces back to this dependent type by saying, for any path, we just take the base point, which was an element of this fibration at north, and we transport it around this path. And this is what we couldn't do until we had the fibration over the whole of the suspension. So this is the payoff of that. And then one goes by methods exactly like these for about another slide's worth. One can prove that m and n are mutually inverse, And so each of these maps, M or N, is an equivalence, and in particular, in the special case of the fiber over north, we got the one we first thought of. So that completes Freudenthal, and the first immediate payoff we get, coming back to spheres, is that since the spheres are reasonably connected, and each one is more connected than the last, and that's not too hard to show, that the n plus kth homotopy group of a circle doesn't depend on n, so that once n is big enough. So this was the diagonals of the chart which Dan brought up, and we'll see again in a moment. So once A is at least k plus 2, it's connected enough to apply Freudenthal, and so one can, from the equivalence of the truncations, unwind the equivalence of homotopy groups. And in particular, as a special case, we can now use this to get that pi n of Sn is exactly the integers for all n at least 1. And this is what we saw in Dan's part. The first case, n equals 1, we used the universal cover. For n equals 2, we got the long exact sequence of the Hopf fibration from Guillaume. And then for n at least 2, we're now into this stable range. So when we hit 2, we're into this stable range where Freudenthal applies and bumps it up from 2 to 3 and onwards the whole way. So this gives us it for all n. So now just coming back to the chart that Dan gave us at the beginning, we can look at which bits have we gotten proved in homotopy type theory. Certainly everything below the diagonal is we've got everything in the first 2 rows is straightforward. And then we've seen today enough to get this the whole of this first diagonal, and also a mention of pi 3 of S2 from the long exact sequence of the Hopf fibration. The parts that are shaded in grey or that are somewhat boxed in grey are things which were somewhat closer to having fully proved and formalized in the homotopy type theory. These, by the Guillaumes, there exists an n, and we still need to compute this n and check that it is what it should be. But we've somewhat got that. And then along this row, we know that these 2 rows are equal, and these diagonals, we know by Freudenthal that they stabilize, but we don't yet have the initial values to propagate along them. So so this kind of shows on the homotopy groups of spheres, using that as a yardstick of what we've got. This is what we've got at the moment. But I want to also, before wrapping up, flip briefly through a few of the other results that we've also got. So not just for those who do know these results, to see what they are. So the James construction is a refinement of the Freudenthal theorem, which decomposes the loop space of the the suspension as a filtration by increasingly connected maps, including into it as a limit of certain spaces one can concretely construct from X, where the connectedness grows, and so these are getting better and better approximations to the loop space of the suspension. The Blakers-Massey theorem, which is a generalization of Freudenthal that calculates up to connectivity path spaces not just in suspensions, but in more general homotopy pushouts. So it's another place where one gets additivity of connectedness. You take a homotopy pushout of I and j connected maps, then the map from the fibers of this into the path spaces of the pushout, or equivalently from this into the homotopy pullback, is I plus j connected. The Van Kampen theorem is another tool talking about a particular range of pushouts. It's a classical theorem saying that taking homotopy groups of certain pushouts of spaces corresponds to certain pushouts of groups or groupoids. The classical theory of covering spaces is a very nice kind of very well understood theory, and it all seems to transfer over very smoothly to this setting. So you can say a covering space is just a family of 0 types depending over a type, and then one recovers in particular something like the classical theorem that covering spaces correspond exactly to sets, so 0 types, with actions of the fundamental group. Eilen-Bergman-Klein spaces, another very classical construction. One can take, so it's a kind of inverse to the homotopy, or adjoint to the homotopy groups, one can take any group and stick it directly into a homotopy group. One can say, for every G and N, there's a space whose nth homotopy group is exactly G and no homotopy groups anywhere else. And these, classically, the building blocks of one of the approaches to cohomology. And so this gives us an approach that we can use to cohomology for types in the synthetic setting. So those are just a kind of highlights of the main things that we've got recently, some of the headline results. But looking at it, just going back to see how kind of nicely and smoothly this has all worked, generalizing here. Where we were at the beginning of this term, in doing the computer check proofs in this setting, in formalizing things first by hand in the type theory and then computer checking them, at the beginning of this term, we had just kind of started to get the setup up and running. We had that pi1 of S1 was Z, and we had the proof that the lower homotopy groups were trivial. And then since then, we've now extended it to a fair range of theorems, I think. So thanks very much for listening.
I'm wondering if there's any way of rigidifying type theory to distinguish homeomorphism types, because some of those total spaces are not homeomorphic. And what are some thoughts on that?
So for now, we can only do homotopy theory, not up to homeomorphism. And it's not really clear. Maybe we can do some kind of rigidify to get homeomorphism, but it's really not clear. It seems to be very tied to homotopy theory, at least for now. So there is some notion of infinity topos, where you can do all that in any infinity topos. And I think there is some notion of topological infinity topos, which talk about homeomorphism, things like that. But this is really work in progress. We don't know, maybe.
So type theory is not fundamentally blind to things above the homotopy level. Like it could conceivably see those things.
You could do it in a very, very different way.
Yes. Yeah.
That's what we talked about. That's why they talked about infinity group points rather than spaces. It's really about
questions of terminology. Why synthetic rather than axiomatic?
Partly because of the kind of an analog with something like synthetic differential geometry. I don't know. It has a slightly different flavor, maybe. I'm not sure.
Because I remember Hannah Koch once said that synthetic differential looks for artificial, like synthetic material.
Synthetic flavorings in your food or something, yes. High fructose corn homotopy theory or something.
I have another question for Dan.
Yeah.
So an alternative presentation for the circle type would have had two objects
Yep.
and two proofs.
Yep.
Saying that those
Yeah,
were
you can prove that that's equivalent to the 1 point homotopic too. Yeah.
Is there any way in Koch or in other means to recognize sort of a skeleton for a type?
Maybe. So there's work on doing that kind of like introspection on data types. We haven't tried to apply any of that to homotopy type theory yet, though.
But at the same time, that would be very much the skeleton of a presentation of the type, not the skeleton of the type itself.
Yeah.
And one shouldn't expect to be able to get the skeleton of just a type without extra presentation data.
Yeah.
That's typically something which it can't be made natural, and so one shouldn't be, yeah.
Which of these results has been formalized in one of the proof assistants?
The ones in bold? We are hoping someone would ask that.
Are there any principal obstacles
think it's just a matter of time. It's a
And of people working on that.
And of proof automation.
But time is, when you say a matter of time, is it like the Fay-Thompson theorem, which took 5 years? Or is it like
No.
a matter of you guys sitting down for a week?
No,
Closer to that. More than a week, but
It's more
yeah.
Like a month each.
well,
less than a month.
a month for all of them, I guess.
a month
Yeah.
or
Yes.
so.
Yeah.
Yep.
I have a question with the type theory has a whole set of foundations that we know of, but there is this higher inductive types that you've been using a lot, but what is the trust in that?
So you mean semantically? Yes. So higher inductive types. So a bit of background here for those who haven't been at one of the ones where we discussed this before. Higher inductive types are, and univalents are both newer principles added on top of an existing type theory. And so the existing type theory has comparatively well-studied semantics and models which let us be confident that it's at least as consistent as classical foundations. How confident are we in the similar kind of consistency and in the semantic meaning of higher inductive types in univalents? We're pretty confident. We have the range of models we have for them is not yet, I think, as wide as the full range of models we have for the base type theory, but it includes at least the settings we mentioned at the beginning of simplicial sets, and it includes, and Mike could give the precise conditions here better than I could, a reasonable range of Quillen model categories. And yes, and conjecturally and heuristically, we hope that that should extend to infinity topoi, but that's very much still a heuristic statement or a conjecture at the moment.
We weaken the univalence axiom slightly, then it does. We know it does work in any of the different.
Okay, right, great. Yes,
That may
that's
not
true.
be very reassuring, though, from a more practical point of view, asking how sure are we that it's consistent to say, well, we know it holds in any infinity topos.
But I mean, it's a model in a classically constructed setting. It's an analytic model of the synthetic theory. So there are,
It's consistent with set theory.
yes,
Yeah, so I think that's, yeah.
yeah, exactly. Yeah.
So at least this is what it's-
Yeah.
The fact that, for example, yesterday the proof assistant was inconsistent, we shouldn't worry about that. Right?
That was an implementation issue. It is a.
Okay, if there's one more thing, since this is the last regularly scheduled seminar, I do want to reiterate Steve's thanks to the Institute and Vladimir for putting this year together. I think that a lot of this stuff that we saw today would not have happened if we hadn't been in the same place talking to each other. And then I think we should have a big round of applause for Vladimir